Wenzel will present how monitoring can influence lifecycle engineering. An example of lifecycle software will be shown where changes in measurement or in management affect the lifecycle curve and therefore predict remaining lifetime in real time.
Okay, thanks a lot. So I'm wirelessly connected to our database. So this is our homepage. We can go to our web interface where we have all our monitoring systems online. In Korea, in Ireland, in Sweden, nothing in the United States. And we can, for example, have an online look on several of our channels, whatever we are interested in. So this is the actual record of an accelerometer on Ruhr Bridge. This is one of the major bridges in Austria. So the viewers that have been at our summer academy last week have seen it. It allows you to give an indication how the bridge looks like, and there is a sensor layer and such things. But this is not the most interesting. The system also computes on-site, for example, diverse correlation diagrams. We have so-called key performance indicators. This means we measure performance of the structure, and if it's a nice diagonal as it is here, everything is safe and lively. We also compensate, for example, for temperature, because this bridge is in the high mountains, so there is a strong winter and such things. We can further look into patterns, for example. It takes a while until you know this comes from Austria, and we are sometimes not that quick. So we compute, for example, weekly patterns. We compare that with the patterns we had, let's say, in the year 2009. We do this since about 2 years. And we compute several of these key performance indicators and feed this then into another software, which I will demonstrate now. This software allows some assessment of structural health in various form. We have three main elements. One is the loading, which is in the middle. Then we have visual inspections, or every expert input, for example, and on the right side we have monitoring. So this is a lifetime degradation model, and we can play around it. Now we have 100% load, for example. We can look what happens if we put 120% of the load. You can see that the curve has changed. Unfortunately, I don't see the full screen here, where I should be able to see here you see the years of life, of remaining life, and here you see the money you have to invest. So if I put, for example, 200% of the load on it, oops, the bridge has collapsed. But here in Stanford, retrofit is very easy. Just go back. What I can do here also is, here we put our monitoring results in. For example, this bridge has a very bad vibration intensity. This means high traffic produces a lot of vibration. We can, for example, if we get better data in and reduce the vibration, we can earn 4 years of lifetime. But on the second figure, on this figure here, you see how much money that costs. Life costs money, unfortunately. And if we have then expert input, and if we improve our structure, we can earn lifetime. It is as simple as that. So in the end, if we retrofit it perfectly, we can probably earn, well, now we have already earned 11 years of life. But it has cost us some money, as we see here. And unlike humans in bridges, we are able to buy additional years of life. I would be a rich man if I could transfer this to human health monitoring. Thank you.
Thank you very much. We have some time for questions. Okay, one question there.
What is your estimation of the remaining life? Could you provide quantification of uncertainty in this prediction?
Yeah, there is, well, we don't have it on the screen anymore, but there are the upper and lower bounds giving us the uncertainties. And the major advantage of monitoring is that the uncertainties get smaller. So we can much better calculate our key performance indicators and therefore get better results. So this is very helpful. And finally, it saves money because with less uncertainties, better decisions will be made.